All right, so this celestial theodolite has been going on for a good 6 months now, and I think I've reached the stage where it's kind of pointless engaging with Alan and Shane. So I'm going to make a short little series, maybe 3 or 4 videos, just going over the main points. And this video is going to show that in order to quote unquote prove the flat Earth, they have to borrow globe math to do it. So hopefully you're all aware of what the celestial theodolite is by now. Basically, they record the time that a star is occluded behind a mountain, perform some fuckery in stellarium to get an angle, and then they compare that angle to the raw flat Earth trig. So you've got the observer over on the right here. He's at about 2,074 meters above sea level, and the mountain that occludes the star is Pikes Peak at 4,300 meters, and the distance is 50.7 kilometers. So the raw flat Earth angle, which assumes that flat baseline sea level, gives an angle of 2 degrees and 31 minutes. And that's how it should be done, right? Because the geometry you use is dictated by your model. But to get the raw angle on a globe, we have to incorporate 8 inches per mile squared in drop. And over that distance of 50.7 kilometers, that makes the mountain about 202 meters lower relative to that 50.7 kilometer baseline. So we get a lower angle of 2 degrees 17 arc minutes. And just for simplicity, we're ignoring refraction for now. So once again, the model you use dictates the geometry. So getting back to the flat Earth prediction, they obviously don't incorporate 8 inches per mile squared of drop because that would be using the globe. So let's look at the other numbers they're using. So the elevations of Pikes Peak and the elevation of the observer will be the same regardless of the model. But where did they get that distance of 50.7 kilometers from? Well, they've made no secret about it because way back in February, Heffron has been openly using this website to calculate the distance between his house and the mountain, and it says explicitly, all these formulas are for calculations on the basis of a spherical Earth, and it gives you the great circle distance between 2 points. And as much as Alan and Shane like to throw the word graticule around, it doesn't change the fact that the model you use dictates the geometry. If you think the Earth is flat, then you need to use planar geometry for your distances as well. What Alan, Shane, and Heffron are doing is using a sphere for distances, but a flat Earth for the elevation angle. And that seems a little cherry-picky to me. So let's have a look at the geometry for getting the distance between 2 points on a sphere and compare that to the geometry on a flat Earth. So let's have a look at the Great Circle route between New York and London. There we are. Let's turn off the map just so we can see what we're looking at. There we go. So this is what the Haversine formula, or the spherical law of cosines really, is doing to calculate that distance. So there are 3 sectors of 3 different circles here, and all of them have their center at the center of the spherical Earth. So the first one in green is from the North Pole down to New York, following the same line of longitude. And since we know how many degrees of latitude there are from the North Pole down to New York, we know the length of that arc. Similarly, the blue sector is a slice of a circle from the North Pole down to London, following its longitude line, and we can also work out the length of that arc. So what the Haversine formula, or the spherical law of cosines, does is solve that spherical triangle by working out what that red angle is at the center, and then basically multiplying that by the radius to get the arc length, which is the distance between the 2 points. So you can see up in the top left up here that the angle is 0.8695 radians. Multiply that by the radius of the spherical Earth, and you get a result of 5,539 kilometers. And here's a website I found just to double check my geometry. So instead of putting linear distances in for the sides, we can just use the equivalent angles. And side A is just the degrees of latitude from the North Pole. and New York, and side B is the degrees of latitude between the North Pole and London, and angle C is the difference in longitude between the 2 points. We hit calculate, and it gives us a distance between the 2 points of 49.82 degrees. How much does that equate to in kilometres? Well, if we assume a radius of 6371, then it works out to be a little over 111 kilometres per degree. So we multiply that out, and we get 5,539 kilometres, just like I got in the visual demonstration. Okay, so now let's look at the geometry of a flat Earth. We're going to do the same two cities. So we're going to fly from New York to London. And obviously, since the Earth is flat, then that dictates what the geometry must be. And in this case, it's a very simple flat triangle. So we're not going to use the spherical law of cosines. We're going to use the planar law of cosines. So, same as before, we know the distance from the North Pole to New York and the distance from the North Pole to London. And we also know the angle formed at the center, which is just the difference in the longitudes. And the result is 5,909 kilometers, which is about 400 k's further than it is on a globe. And just for shits and giggles, if you use this flat Earth geometry to calculate the distance between the observer and Pikes Peak, you get 57 kilometers, not 50.7. And that makes your new angle not 2 degrees 31 minutes, 2 degrees 14 minutes, which is lower than the globe angle of 2 degrees 17 minutes, again, ignoring refraction. And here's another online calculator, just to double check the result between New York and London. So once again, I've used the difference in latitude between the North Pole and New York for side A, and then same again for side B. And then solve for side C. We get 53.18 degrees. We multiply that by 111 kilometers per degree, and we get the same value, 5,909 kilometers. Now, you've probably noticed there's a slightly different multiplier than the previous calculation, and that's because I've used the original definition of the meter here, which is 10,000 kilometers between the North Pole and the equator, and that isn't exactly the same value you get with a radius of 6371 kilometers. So, first question for Shane, Alan, and Dr. Mike. What does the Earth look like if you zoom out? If it looks like a ball, then you're quite welcome to use globe geometry. But if you think it's flat, then you need to use planar geometry. Second question. There are two propositions on the screen. What you guys are doing is obviously number one, you think the Earth is flat, but you assume globe geometry to get your distances, which means you treat latitude as the angle, from the plane of the equator, and your longitude as the angle around the polar axis passing through that equatorial plane. The opposite of that position is that the Earth is in fact a globe, but you should somehow assume that it's flat to calculate distances. So in this graticule, your latitude is proportional to your distance from the North Pole, and longitude is the angle around that single axis at the North Pole. So the question is, what makes one of these right and the other one wrong? You've already seen that latitude and longitude can be easily represented on both a globe and a flat disk. So what makes one correct and the other incorrect? Or another way of phrasing the question, is the globe a distorted projection of the true flat Earth, or is the flat Earth a distorted projection of the true globe? I think we know the answer. The globe gives accurate distances and the flat Earth doesn't. And it's honestly one of the big reasons I can't take you guys seriously anymore. And just to finish up, as I'm sure you're all aware, the Ether Cos boys have blatantly stolen Walter Bislin's model, as well as stealing the globe for calculating distances, but they also have the fucking audacity to use stellarium to get their star angles. And surprise, surprise, stellarium uses spherical geometry to calculate those angles, But that will have to wait for part 2.